Okay, yeah. Hi, everyone. My name is Yang He from Fraser University. I'm going to present our paper, Graphiti, Bridging Graph and Relational Database Queries. It's a joint work with Ruijie, Fang, and Işıl Dillig from University of Texas at Austin, and Yuepeng Wang from Fraser University as well. Over the past decades, graph databases have become increasingly popular in both industrial and academia due to the flexible data models. Nowadays, we have many graph database management systems, such as Neo4j and Cosmos DB, designed for graph-centric applications like social network and recommendation system. Therefore, many developers migrate relational database applications to the graph databases. However, transition between graph and relational databases requires rich expertise, and writing graph queries that are equivalent to the original SQL query is error-prone. For instance, many Stack Overflow posts reveal that translation between graph and relational queries can be quite challenging due to the misunderstandings of aggregation semantics, joins versus relationships, and other complexities. However, to our best knowledge, there is no prior method to check the correctness of migration, resulting in subtle bug hidden in this post and even the official tutorial. In this work, we propose a method to check equivalence between graph and relational database queries. In a migration setting where developers have refactory relational tables in a graph structure and a relational SQL query in the Cypher language, our goal is to ensure these two queries consistently produce the same results. However, this problem is non-trivial and presents a natural question: what does it mean for two queries to be equivalent? If we don't know the relationship between the data stored in graph and relational databases, then equivalence could be easily-defined. This requires us to find a mechanism to align relational and graph databases. The solution is to introduce the concept of a user-provided transformer, which is inspired by schema mapping from the database community. It specifies data equivalence between graph and relational databases, and thereby enable us to define query equivalence. Using user-provided transformer as specifications sounds good, but how to specify these transformers? The insight is that we can naturally specify transformers via data log rules. Even though graph databases don't have explicit relations, we can think of each node and edge type as a relation. To make this concept more concrete, let's consider a user-provided transformer example in practice. Here, we have a graph database where employee and department nodes are connected via work edge. Specifically, it indicates that both Alice and Bob work in the IT department. In contrast, the relational database only has two tables, employees and departments, with a foreign key DID to maintain the relationship. It also indicates that Alice and Bob work in the IT department. To ensure these two databases maintain the same data, we use a user-provided transformer to align their structures and semantics. Take the work edge as an example. This rule specifies that for each path from employee to department through a work edge, there is a corresponding rule in the employees table. Now that we have a way of specifying data correspondence, we can formally define equivalence as follows. Let Q be a graph query of a graph schema S, and Q prime be a SQL query of a relational schema S prime. These queries are equivalent modulo user-provided transformer T, if and only if, for any graph instance of the graph schema S and the relational instance of the relational schema S prime that satisfies the transformer T. Executing the two queries on this instance generates the same results. Since this formal definition is a bit abstract to understand, I will explain it in more detail. Suppose that we have an arbitrary graph database and a relational database that satisfy a user-provided transformer. A graph query produces a tabular result when executed on the graph database. Meanwhile, a relational query returns another table when operated on the relational database. If these two resulting tables from both queries are identical, then these two queries are considered equivalent. Now, we have an equivalent definition between graph and relational queries. But how can we check it? A strawman idea is to simply encode query semantics in SMT and directly check the definition. However, checking equivalence in this way may present a problem. We need an SMT encoding that can simultaneously describe graph and tabular data. Unfortunately, from our preliminary experience, such an SMT encoding doesn't work well in this verification task. To solve this issue, we reduced the original problem to sequence checking using a correct by construction transpilation technique. Concurrently, we first transpile the graph query into a relational query, and then leverage the existing method to check equivalence of two relational queries. If we can automatically transpile graph queries into relational queries, why do we need to verify equivalence between these two relational queries? The reason is that a graph schema only can be transpiled to some relational schema, but it may differ from the target relational schema. More specifically, let's consider this example. Given these two schemas, it's difficult to transpile a graph query over this graph schema to a relational query over this target relational schema. Instead, generating a relational query over a relational schema that has three tables corresponding to this graph schema is more straightforward. Therefore, the first insight is that transpile a graph database into a relational database of a certain shape is easy. We capture this shape using the notion of a standard transformer, which directly maps nodes and edges to relational tables with the same attributes. Additionally, graph queries can be translated to relational queries over these new relational tables. The second insight is that transpilation reduces the original problem into an easier sequence checking problem over different schemas. This area has been well studied, and we have many tools can check equivalence by verification or falsification. More concretely, here is how our method works. The original verification task aims to verify equivalence between graph and relational queries. Since this direct verification problem is challenging, we reduce to a well-studied problem, sequence checking. Our method first derives a so-called standard transformer to convert the graph database into an induced relational database. Then, it applies a correct by construction transpilation technique to generate a transpile relational query that is provably equivalent to the original graph query modulo this standard transformer. Based on these two transformers, we can construct a registry transformer to ensure data equivalence between the induced and the target relational databases. And it also serves as a specification for the subsequent verification process. Finally, an off-the-shelf sequence checker can be used to check equivalence for these two relational queries. Now, let's walk through an example to better understand how our method works. Suppose we have a graph query over this graph schema, and a relational query over this relational schema, and a user-provided transformer to align these two schemas. These two queries are equivalent modulo this user-provided transformer. The answer is yes. And I will show you how our methodology proves this. Our method first automatically derives a standard transformer. Its basic set of rules to convert nodes and edges into relational tables, where attributes become columns. Consider this a standard transformer. By applying to previous graph database, we can construct three induced tables corresponding to the nodes and edges in the graph. In general, standard transformer converts any graph database into a rational one, which means our method can check equivalence for queries that conform to arbitrary schemas. Next, we transpile the original graph query into a equivalent relational query, module this standard transformer. Based on the standard transformers, we define correct by construction translation rules and prove them correct in our paper. I won't explain how translation works. Please refer to our paper for more detail. For this example, a translation will produce a transpiled relational query that is provably equivalent to this graph query modulo the standard transformers. Before checking the CQ equivalence, we must construct residue transformer to align the induced and targeted relational databases. Recall that residue transformer describes data equivalence between two relational databases and serves as a specification for the CQ equivalence checking. And we can automatically infer a residue transformer from user-provided transformer and a standard transformer. For example, the rule from the user-provided transformer preserve the same relationship between the work edge and the employees table. And the rule from the standard transformer ensure data equivalence between the work edge and the work prime table. Then we can infer a residue rule that preserve the consistent relationship between the work prime and the employees table. Similarly, we can derive other rules for the remaining table in the induced relational database, namely employee prime and department prime. Conceptually, residue transformer tells the CQ equivalence checker how to align two relational databases over different schemas. With all these components in place, we finally can check equivalence for these two relational queries. Using existing CQ equivalence checker, we can prove this transpiled relational query is equivalent to this target relational query modulo the residue transformer. That's to say, the original graph relational query pair is equivalent modulo the user-provided transformer. This is the whole verification process about this work. Now, let's focus on the evaluation part. We implement a tool called Graphiti and instantiate with two existing CQ checkers. The first one is a bounded model checker called VerEco, proposed in 2024. It reviews equivalence by generating counterexamples and produces no false positives. The second checker is a deductive verifier named Mediator, proposed in Popo 18. It proves equivalence for CQ applications and produces no false negatives. In this work, we explore two research questions. Can these instantiations of Graphiti find bugs and verify equivalence? We evaluate Graphiti on about 400 equivalence verification tasks between Cypher and CQ queries. These tasks are sourced from Stack Overflow posts, online tutorials, prior literature, and GPT translations. When using VerEco as a backend, we can check equivalence for all benchmarks. Among them, 376 are proved equivalent with an average bound of about 20, and only 34 are refuted with counterexamples in an average refutation time of 23.4 seconds. We mainly expected all these counterexamples by executing them on MySQL and Neo4j databases, and confirmed that they were all valid and can produce different results. This demonstrates that Graphiti can identify subtle bugs in a short time. The main takeaway from this experience is that using a bounded model checking backend, Graphiti can identify 34 bugs. When using Mediator as a backend, we only support less than half of benchmarks. Among this supported pair, we can prove 152 are equivalents, which are also confirmed by bounded model checking. mediator return unknowns for the remaining benchmarks because it needs to find a complex invariant for long join chain, which leads to expensive SMT queries and thereby triggers timeouts. The average running time for these verification tasks is about 70 seconds. The takeaway that using a deductive verifier, Graphiti can prove equivalence between about 80% of supported benchmarks. Overall, in this work, we propose Graphiti, the first technique for reading about equivalence between graph and relational queries, modulo user-provided transformers. This is the end of this talk. Thanks for attention.
Let's see. Let's start with the person who didn't ask previously. Yeah.
Hello, Amir from Edinburgh. Very nice presentation. I was wondering to what extent the features of the Cypher language you're supporting. In particular, do you support variable length path or optional match?
Okay, yeah. We might extend our Cypher query for variable length path matching, and it can be implemented with recursion expressions. Okay, yeah. As for the option match, we already considered it.
Okay, yeah. In particular for the variable length path, so you need to support recursion in SQL. That makes the equivalence of SQL queries very complicated. Do you have any thoughts?
Yeah,
about
true.
that? Okay, thank you.
Thank you.
Hi, thanks for your presentation. And I want to ask that, is it hard for a user to write the transformer because when the graph database becoming more complex, I think maybe it's harder.
Maybe, yeah. Say the average transformer size consists of about 6 rules, and from our experience, writing a transformer for a benchmark maybe cost 1 minute. I think it's acceptable.
So the transformer size is linear to the complexity of the graph schema, or it's fixed?
No. Yeah. It depends on the graph and the relational schemas, because you need to write a rule to describe how you map data correspondence between this graph and the tables.
Yeah. So have you done any user study, like?
No.
Oh.
Yeah. Maybe we can do it in the future.
Oh, thanks.
Yeah.
Thank you for the talk. So it's known that the graph model is an instance of the relational model. So it's nice to see that you can do this equivalence checking between different models. So one question I'm curious is actually about what kind of real world use cases you can think of, because it does not seem like I don't know many project that switch from one model to another. It's more like, when you start a new project, you pick maybe a more novel data model. So do you see are there projects in real world that does this switch?
Let me think. I think there's a project called Apache Edge. They use a graph API to manipulate relational databases. Maybe you can check it. Yeah.
I see. And maybe a related comment is, I think there's some graph databases that provide the graph query, but they're implemented using the relational databases. Maybe there's another way where you can have a relational database where you accept relational queries that are translated to graph queries.
Yeah. Thank you.
And why don't you go plug in while we close things out here. Any last audience questions? Let me try to fit in one of mine. Is it the case that you're only supporting non-recursive data log programs in transformers?
Yeah. Right now we don't support that.
Got it.
Okay.
Makes sense. Okay, let's thank the speaker again.